Welcome back to astronomy. Let's talk about orbits and gravity. Last time we talked about retrograde motion, in which planets tend to turn around and move backwards across the celestial sphere, as opposed to their normal eastward motion. One of the scientists who made a large number of measurements of planets, including Jupiter and Mars, was Tycho Brahe. Now, he didn't have telescopes. He had to construct these large instruments to be able to precisely measure the positions of planets, their right ascensions and declinations. And he did so better than any other astronomer or scientist at the time. One of the things that Tycho and other astronomers noticed is that the sun and the moon followed the ecliptic. The moon not so close, about 5 degrees off of the ecliptic. But even the planets would generally follow the ecliptic, and that would take them through the zodiac constellations. They would wander through these zodiacs in two ways. One of them is the normal eastward motion that I talked about, and then occasionally the westward retrograde motion. Pretty much all astronomers knew about that, but it was hard to determine which was correct. Was it the ideas of Ptolemy or Copernicus? Here's some observations from 1994 of Mars day by day as it goes through Gemini. And then you can see here on January 4th, it turns around, goes into retrograde, and then back toward direct motion like this. So the question is, did Tycho's observations support the idea of Ptolemy and his geocentric model with difference in epicycles, or did it support the theory of Copernicus with heliocentric model and parallax? And it turns out that his precise measurements of the planets did not match up with either one of these. Although we know that today, the heliocentric model is a better model, or the correct one rather, it turns out that Tycho's precise measurements did not exactly match up with Copernicus. And that's because these orbits were not circular, as we'll find out when we look at the work of Johannes Kepler. Johannes Kepler modifies the ideas of Copernicus, and he describes the planets and their orbits not as circular or circles upon circles, but rather elliptical orbits. So with his 3 laws of physics, Kepler's first, second, and third law, we call them, he describes the orbits of planets as well as their speeds as well. So you can look at the 3 laws of Kepler in 3 ways, and we'll do that in a moment. One of them is talking about the shape of the orbits. That's part A, or Kepler's law, number 1. Kepler's first law, rather. Kepler's second law is about how fast planets move. And then Kepler's third law relates the orbital period to the semi-major axis. But let's get into them one at a time. When you draw an ellipse, what you do is you have basically a fixed position here on a piece of paper. You can put tacks in there, tie a loose string in a loop around it like so, and then hold the pencil inside of that string, pull it tight, and then the shape that you're going to make is an ellipse. And so the distance between the center of that string and between the 2 tack marks right there and the outside edge, this distance over here, is called the semi-major axis. So Kepler's first law, simply put, it's about ellipses. It says that planets move in elliptical orbits around the sun, with the sun at one of these focus points, and that means where the tack is right there. So that's what his first law observed. If we look at the orbits of the planets, they follow that, but not only that, you can see the blue ones here are the orbits of asteroids, and the red ones are the orbits of comets. All of these orbits are conic sections, meaning that they're either circular, elliptical, parabolic, or hyperbolic. Kepler's second law deals with the speeds of orbits. He was more of a geometrical kind of guy. In other words, he taught mathematics, and his statement was that a planet with a line joining the planet and the sun will sweep out equal areas in equal intervals of time. So if the time between these 2 endpoints of this shaded blue area is, say, like 30 days, and this is 30 days over here, then the area of this blue area on the right should equal the area of the blue area on the left-hand side. This closest point to the sun, you can see sun is at one of the focus point. The closest point to the sun is called the perihelion, and the furthest point is called the aphelion. And so the only way that this could be 30 days here and 30 days here is if it goes slow here, if the planet moves slow out here and fast there. And that's what he observed about planets, is they almost slingshot themselves around the sun, where it's going slow out here, speeds up, goes fast here, then slow out here again. That's certainly true of comets when they get far away from the sun and they are allowed to refreeze, but then speed past the sun when they come close to the perihelion. You might even use a mnemonic like P, meaning closer in proximity to the sun, or A, as in far away from the sun. That might help you remember the difference between perihelion and aphelion. Mathematicians and astronomers use the word eccentricity to describe how circular or oblate an orbit is. Here, the eccentricity for a circle is just 0. But then as you begin to move these two foci further and further apart, you get them more eccentric and then highly eccentric. And you can see that it has basically something to do with the semi-major axis right here and its relationship to the spacing between the two focal points there. If you put the focal points on top of each other, you basically end up with a circular orbit. Then on to the third law. Kepler's third law is again a mathematical argument. It deals with that semi-major axis as well as the length of time it takes a planet to move around the sun. That's called orbital period. So mathematically speaking, he said that the orbital period squared in years is equal to the semi-major axis cubed if you measure A in astronomical units. It's basically saying that the further a planet is away from the sun, the longer it's going to take you to go around. For example, Pluto at some 40 astronomical units away from the sun is going to be 150 years for it to go all the way around the sun one time. So let's look at an example of Kepler's third law. The semi-major axis is 5.2 AU. That means that Jupiter is 5.2 times the Earth-Sun distance. And then if you look at Kepler's third law, p squared equals a cubed, take the square root of both sides, you get p is equal to a cubed over 2, or a to the 3/2 power. You can put this 5.2 in there, and then you find out that the orbital period of Jupiter is 11.86 years. And so this matches up. If we measure this distance here and measure that time right there, we find that this relationship holds true. P squared is equal to a cubed. Recall from earlier in other videos that an astronomical unit is the average distance between the Earth and the sun. It's 93 million miles, or 8.3 light minutes. It takes 8.3 minutes for light to get from the sun to the Earth. That means if something were to happen on the sun, we wouldn't know for 8.3 minutes. Looking at other laws of physics, we find that Newton comes after Kepler, and he's able to explain why Kepler's laws of physics are correct. Looking at Newton's first law, he states that objects that are in motion will tend to want to stay in motion, and objects that are at rest will want to strive to remain at rest. That's the so-called law of inertia, meaning that in the absence of gravity, if a planet is moving, it will want to move in a straight line if you turn off gravity. And if a planet is at rest in the absence of gravity, it's just going to want to stay there. And the more massive an object is, the more inertia it has. All right, these are all in Newton's Principia, all three of the laws that we're discussing here for Newton. Newton's second law says that the force on an object is proportional to its mass times its acceleration. That means that if you have a gravitational force, for example, acting on a mass, it will tend to cause it to accelerate. In our case, it causes it to accelerate. If it's in orbit, it'll cause it to turn. So it keeps, the gravitational force keeps planets in their orbit by changing the direction of their motion. That's one form of acceleration. Newton's third law deals with, it also deals with forces. It says that for every action, there's an equal and opposite reaction. That means that if the Earth exerts a gravitational force on the moon, that must mean the moon exerts a gravitational force on the Earth. So looking at these three laws, if you're looking at just some word to keep them straight, you can say that the first law is the law of inertia, the second law is F equals ma, and the third law is action reaction. There is another law, but it's not really numbered. It's also found in Newton's book, this Principia, and it deals with the gravitational force between masses. What he demonstrates is that every mass exerts a gravitational force on every other mass. And so the mathematics looks something like this, that the force of gravity is equal to some universal constant capital G times the mass of those two objects. Now that could be the mass of the Earth and the mass of the moon. And this right here would be the separation between the centers of the Earth and the moon. However, this could really be you and your car. It's basically saying that you would take your mass and your car's mass and the separation between your centers, and there is actually a gravitational pull between you two. Now, the Earth's gravitational pull overwhelms all of that, so you'd have to put you both out in space. You say put yourself in a spacesuit and put your car out there in space, and if you're far away from other objects, then you all would, not you all, you and your car would slowly drift toward each other due to your gravitational attraction between you and your car. Now, it's a very weak force, this constant of proportionality right here, capital G, is called the universal gravitational constant. It's 6.67 times 10 to the minus 11th. Newtons is the unit of force. Meters is what's used for distance, and kilograms squared because we have two masses up there. So it's a rather small number. So let's look at some potential gravity questions. The first question is, did the moon exert gravitational forces on the Apollo astronauts? And the answer is yes. Now, I remember going to a psychology class when I was in college, and I remember the professor said that there was no gravitational force on the moon. And then my friend, who was also a physics major, asked the psychology professor, did you say that there's no gravitational force on the moon? And he said, yes. And then my friend said to the psychology professor, well, then why did the Apollo astronauts, how were they able to stay on the surface of the moon if there's no gravity? And my professor said, and I quote, they stayed on the surface of the moon because the Apollo astronauts were wearing heavy boots. Now that's a little misleading answer there. There really is a gravitational pull on the surface of the moon. It's just weaker. It's 1/6 of the gravity that you would have here on the surface of the Earth, meaning that if you weigh 180 pounds here on Earth, that you would weigh 30 pounds on the moon. So you can certainly jump a lot higher there. What kinds of objects can exert gravitational forces on other objects? And the answer is anything with mass. So it could be like a pencil and a grain of sand, or it could be like a black hole and another galaxy. Anything that has mass is going to be attracted to anything else that has mass. Now the constant G is a rather small number. You can see it's times 10 to the minus 11th. So my new question is, what kind of objects can exert strong gravitational forces on other objects? And the answer is, it's got to be, let me show you this equation again. It's got to be something large. If this is a small number, you have to have a really astronomical number there, like a sun, a planet, a galaxy. That's the only way that you can get a strong gravitational force. Now, next question involving this universal law of gravitation from Sir Isaac Newton. If the distance between two objects in space is doubled, then what happens to the gravitational force between them? Well, the answer would be it certainly gets weaker. So as you can see here, the more you increase the radius here, the weaker this becomes. In fact, you can go a step further. You can say because it's doubled, you're multiplying this times 2, but then you're squaring it. So we can actually say that it decreases to 1/4 of what it was before, 2 squared. So you can change this question and you say, what if you triple the distance between the two? Then it decreases by 1/9 because triple corresponds to 3. You square that and you get a 9. You could do the same things by saying 10 times the distance. In that case, the gravitational force would be 1/100 of what it was before. All right, let's look at more about orbital motion, some key ideas there. The orbital period and semi-major axis of an artificial satellite can be used to determine a planet's mass. This is actually how we measure the mass of the moon and the mass of the Earth. We launch an artificial satellite into Earth's orbit. We measure the orbital period, measure how far it is away from the center of its orbit, or from the foci where the Earth is, and you're able to calculate the mass. The equation for that, as you'll see in the textbook, is that the mass, it turns out this is in solar masses, is equal to the semi-major axis cubed over the orbital period squared. So this is basically a result of Newton working hard on Kepler's third law and finding out that constant of proportionality really had the mass of the system in it. So this is how we measure the mass of Jupiter. We watch a moon of Jupiter go around Jupiter. We figure out how long, or measure how long it takes that moon to go around Jupiter, take the ratio of those two like that, and you're able to get the mass of Jupiter. This is how we measure the masses of planets, stars, and galaxies, is we have to know orbital period and semi-major axis of some lighter or less massive object that is orbiting them. So Kepler's third law can be derived from Newton's laws. That's how we were able to get that mass equation that we use in astronomy. You also can determine what the surface gravity is. The way that we know that the surface gravity on the moon is 1/6 is because we know we know from a planet's radius and its mass what the surface gravity will be like. We can know in advance what the surface gravity on Mars is like by using this calculation. Now, the surface gravity and the escape velocity are both affected by a planet's radius and mass. It's harder to leave a massive planet. It's harder to escape from the gravitational pull of an object. Well, you can't really fully escape. You can just basically make it out without having to turn around and crash back into the surface. So you have to have a sufficient amount of speed in order to leave the planet. And that can be calculated if you know a planet's radius and mass. Here's the concept of escape velocity. If you don't have enough velocity, then you're going to have to return back and land back on the surface of the Earth. But if you can achieve a high enough velocity, you can leave and then end up on another planet. So that is possible to do that. Here's some review of some concepts we talked about, plus two new items here. Remember that aphelion is the furthest point away, and perihelion is closest in proximity to the sun. Similarly, if you have an artificial satellite orbiting the Earth, then the perigee is the closest point in proximity to the Earth, and the apogee is the furthest point away from the Earth. Newton proposed that you could make artificial satellites. So he was one of the key players in us having artificial satellites orbiting the Earth now. Him, along with John Goddard, the father of modern rocketry, gave rise to all these satellites that we have in orbit around the Earth now. Newton's idea was that if you fire a cannon off of a mountain, that it would make this parabolic path here, and the faster you would have its muzzle velocity, the further around the Earth it would go. And eventually, if you could at least get above the air resistance, a cannonball would fall around the Earth rather than into it. Now, of course, this wasn't high enough. You really have to get above the Earth's atmosphere to get the air resistance down in order to make an artificial satellite. But his concept was accurate in the sense that you could essentially get it fire it at something like 8 kilometers per second, and you're able to have it orbit the Earth. And so here's more figures from your textbook, and also a drawing from Newton's Principia over here. There are thousands and thousands of satellites. Let me pause the video and see if I can find the website that has the current locations of all the satellites. And as I loaded up this page, I heard my hard drive fan start to kick up. So it's doing all of these calculations about all of these tiny dots out here, which are the satellites that were launched into orbit. I'm just going to zoom in on one of these and maybe click on it. You can see that the name of it's listed over here to the left-hand side. See if I can go back over here, zoom back. And you do see that, let's see if I can get it to rotate down a little bit. You do see a ring right around here. These are the so-called geosynchronous satellites. These are launched up to an orbit such that they have an orbital period equal to 1 day. That means that this satellite right here will remain above a fixed position on the Earth. And so it can stay basically staring at that position all the time. It's also used for satellite TV. So if you have a dish on top of your house, it's pointing to a fixed position in the sky because it's pointing at a fixed satellite that is transmitting those television stations back towards you. See if I can see that ring a little bit better. There you go. So that ring out there, a lot of weather satellites, but also telecommunications as well. All right, that is all for today. I'll catch up with you all later.